Hey there! In this video, we're going to talk about eigenvalues and eigenvectors. These terms often sound intimidating to students learning linear algebra for the first time. The words themselves look scary, and the concepts might not seem immediately useful. But actually, they are fundamental to understanding how matrices work, especially in data science. Let's start with the definition. If we have a square matrix A and a non-zero vector x, we say that x is an eigenvector if multiplying A by x results in a scalar multiple of x. That scalar is what we call the eigenvalue, denoted by lambda. In equation form, this is simply A times x equals lambda times x. This means that when the matrix A transforms the vector x, it only stretches or shrinks it without changing its direction. Now, let's see how we can actually calculate these values. Suppose we have a 2 by 2 matrix A with entries 0, 1, -2, and -3. We want to find the eigenvalues and eigenvectors for this matrix. We start by rearranging our definition equation. We can rewrite the right side using the identity matrix I, so it becomes lambda times I times x. Bringing everything to the left side, we get the quantity A minus lambda I all times vector x equals the 0 vector. Since we defined x to be non-zero, the only way this equation holds is if the matrix A minus lambda I is not invertible. And if a matrix is not invertible, its determinant must be 0. This gives us our characteristic equation. The determinant of A minus lambda I equals 0. Let's compute this for our example. Subtracting lambda from the diagonal entries of A, we get a new matrix. Calculating the determinant gives us a quadratic polynomial, lambda squared plus 3 lambda plus 2. Setting this polynomial to 0 allows us to solve for lambda. Factoring the quadratic, we find two roots. Lambda equals -1 and lambda equals -2. These are our eigenvalues. To find the corresponding eigenvectors, we plug each eigenvalue back into our equation. For lambda equals -1, we substitute it back and solve the resulting system of linear equations. We find that any vector where the first component is the negative of the second component works. For example, the vector 1, -1. So, why does this matter? Visually, a matrix represents a linear transformation. Most vectors, when transformed by A, will change direction and get knocked off their span. But eigenvectors are special. They stay on their own line. The matrix simply scales them by the eigenvalue. This property of maintaining direction is incredibly powerful in data science. It allows us to understand the principal axis of data, which is the core idea behind algorithms like principal component analysis. When we find eigenvectors, we're finding the axes that really matter for the transformation. So to summarize, eigenvalues and eigenvectors tell us about the invariant directions of a matrix transformation, providing deep insight into the system's behavior. And that basically wraps up this video. Thank you so much for watching. If you found this explanation helpful, give it a thumbs up, share your thoughts in the comments, and subscribe to stay up to date with everything I post on this channel. See you in the next one. Bye bye.